All right, the last test that we're looking at in this section is the root test. Again, the root test has three cases, just like the ratio test. And now we're looking to take the nth root of our series. So a giveaway to using the root test is that you're going to see your sequence function a sub n raised to the nth power. And by taking the nth root, we can get rid of that big power and see what's really happening with our function. Again, we're taking the absolute value of your sequence function. We're taking the limit again as n goes to infinity. Same three conditions. If your limit is less than 1, then your original infinite series is absolutely convergent, and it will then therefore converge. If my limit, case 2, is greater than 1 or equal to infinity, then my original series is divergent. And if my limit is equal to 1, then the ratio test is inconclusive. We can't determine whether we converge or diverge. So, an example, we have an infinite series. We have, in parentheses, 5n plus 4 over 3n plus 7, all raised to the nth power. Good time for the root test. You take the limit as n goes to infinity of the nth root of the absolute value of the nth power. So the nth root and the nth power will cancel each other out. Again, why are we keeping these absolute value bars? Because when n is an odd power, you run the risk of having negative terms in your sequence. Therefore, absolute value, we want to keep them positive to see if we're converging or diverging. So that simplifies away. Again, since n was starting at 1, we're using all positive values for n. We have all addition and multiplication, which will, again, keep all that positive. We'll take the limit of this sequence function, 5 to the n to the first power, 3n to the first power. When my leading terms have the same leading powers, then the leading coefficient ratio is my limit value. That's from your horizontal asymptotes. So 5/3 is greater than 1, so therefore, greater than 1, case number 2, our original series is going to diverge. Example number 8. Here we have, again, an infinite series. We have 3n plus 1 on the top, 5n cubed plus 7 on the bottom, all raised to the 3n power. So again, definite root test. We take the limit as n goes to infinity of the nth root, not the 3n power, the nth root. So that's only going to cancel out that n right there. Again, my a sub n is inside of absolute value bars. Well, again, everything's being added or subtracted, so we can drop the absolute value bars, raise it all to the third power. And now, again, using your horizontal asymptote rule, if the top power on the leading term is smaller than the top power of the leading term in the denominator, then so smaller, bigger, this is approaching 0. And if this is approaching 0, 0 to the power of 3 is still 0. And 0 is less than 1, so case 1, the series converges absolutely. Example 9, we have the infinite series. We have -2 to the n power over n to the n power. So here, imagine, if you will, since both the top and the bottom are raised to the nth power, we'll just take the whole fraction to the nth power. The nth root and the nth power cancel each other out. The absolute value of -2 is now +2. We don't need absolute value bars around the n because, again, n starts at 1 and counts up to infinity, so we're only putting in positive values, so we're all good here. So this limit, constant on the top, heading to infinity, is 0. So again, that's less than 1. Therefore, by case number 1 of the root test, this series converges absolutely. Example number 10, an infinite series. We have n squared plus 7 on the top, n squared minus 4 on the bottom, all to the nth power. It's a definite root test. Nth root of the absolute value of n squared plus 7 over n squared minus 4, all that to the nth power to cancel those out. N squared plus 7 is guaranteed to be positive, again, using positive 1 and all positives after that heading to infinity. On the bottom, though, we can't guarantee that, so we're going to keep our absolute value bars there. You can still think of this as leading term, powers are the same. Therefore, the leading coefficient ratio, 1 over 1, is going to be my limit. So here, this is case 3 of the root test. Our root test is inconclusive, so we can't determine are we going to converge or diverge. Pretty straightforward. All right, that wraps up our root test and section 9.6.